Hello and welcome to another lecture based on applications of derivatives. Today we shall be discussing about maximum and minimum values of a function in the given domain. Later we are going to discuss the first derivative test for maxima and minima. And finally we shall conclude this lecture by discussing a numerical problem that would be based on the concepts that we are going to discuss in the coming segments of this lecture. So we are going to begin this lecture by discussing the maximum and minimum values of a function in its domain. So starting with the maximum value, we suppose fx to be a real function defined on an interval I, then fx is said to have a maximum value in I if there exists a point A in I such that fx is less than equal to fa for all x belonging to interval I. In such a case, the number fa is known as the maximum value of the function fx in interval I, and the point A is known as the point of maximum value of function in interval I. Now as we can see in this given graph, we have the maximum value of fx at point A whose value is fa at point A. Thus, fa represent the maximum value of fx and the point A is called the point of maximum value of f in interval I. Now let us consider the function f given by fx equal to minus x minus 1 whole square plus 10. Now clearly the domain of function f is equal to r, which is minus infinity to infinity, and we observe that minus x minus 1 whole square is less than equal to 0 for all x belonging to r, which implies that minus x minus 1 whole square plus 10 is less than equal to 10 for all x belonging to R, which means that fx is less than equal to 10 for all values of x belonging to R. Now since f1 is equal to minus 1 minus 1 whole square plus 10, which is equal to 10, therefore fx is less than equal to f1 for all values of x belonging to R. This follows that the expression that f1 is equal to 10 is maximum value of function f, and the point of maximum value of f is x equal to 1. Next we are going to consider the minimum value of a function f in its domain. For this, let fx be a real function defined on an interval I. Then the given function fx is said to have a minimum value in the given interval I if there exists a point A which belongs to I such that fx is greater than equal to fa for all x belonging to I. In such case, the number fa is known as the minimum value of the function fx in the interval I, and the point A is called a point of minimum value of function f in the interval I. Now we are going to consider a graph for this. Here we have a curve or a function defined as y equal to fx defined in the interval I. Now the minimum value of this function fx is at point A and is equal to fa. Therefore the number fa is known as the minimum value of the function y equal to fx in the interval I, and the point A is known as the minimum value of f in interval I. Now in order to find the minimum value of a function, we consider a function fx which is equal to x square plus 5. Now clearly the domain of this function is equal to r, which is minus infinity to infinity. We know that x square is greater than equal to 1 for all values of x belonging to r. This implies that x square plus 5 is greater than equal to 5 for all values of x belonging to r, which further implies that fx is greater than equal to 5, which implies that fx is greater than equal to f0 for all x belonging to r. It follows from this expression and the above definition that the minimum value of the function fx is equal to x square plus 5 defined on r is 5, and the point of minimum value of f is x equal to 0. Now we are going to discuss local maxima and local minima. In the previous section of this lecture, we have discussed about the greatest, that is the maximum, and the least, which is minimum values of a function in its domain. But there may be points in the domain of a function where the function does not attain the greatest value, but the values at these points are greater than or less than the values of the function at the neighboring points. Such points are known as the local minimum or local maximum points, and we can have their definitions as a function which is, let's say, fx is said to obtain a local maximum at point x equal to a if there exists a neighborhood whose points are a minus delta and a plus delta of point a such that fx is less than fa for all values of x belonging to interval a minus delta and a plus delta, or we can say that fx minus fa is less than 0 for all values of x belonging to a minus delta and a plus delta and x not equal to a. In such a case, fa is called the local maximum value of function fx at point x equal to a. Next, we are going to discuss the local minimum value of the given function fx. A function fx is said to attain a local minimum at x equal to a if there exists a neighborhood whose points are a minus delta and a plus delta of a such that fx is greater than fa for all values of x belonging to interval a minus delta and a plus delta and x not equal to a, or we can say that fx minus fa is greater than 0 for all x belonging to interval a minus delta and a plus delta and x not equal to a. The value of the function at x equal to a, that is fa, is called the local minimum value of the function at point x equal to a. Next, we are going to discuss the extreme points, the points at which a function attains either a local maximum or a local minimum are known as the extreme points, and the values of these functions at which the local maxima and local minima is being attained are known as the extreme values of the given function fx. Next, we are going to discuss a theorem which is also known as the first derivative test for maxima and minima. For this, let f be a differentiable function defined on an interval I and let a belong to I. Then x equal to a is called the local maximum value of f if f dash a is equal to 0 and f dash x changes sign from positive to negative as x increases through a, that is f dash x is greater than 0 at every point sufficiently close to and to the left of a, and f dash x is less than 0 at every point sufficiently close to and to the right of a, and the point at x equal to a is a point of local minima point of function f if f dash a is equal to 0 and f dash x changes sign from negative to positive as x increases through a, that is the derivative of the function fx, which is f dash x, is less than 0 at every point sufficiently close to and to the left of a, and f dash x is greater than 0 at every point sufficiently close to and to the right of a. And if f dash a is equal to 0 and the derivative of function fx does not change sign as it increases through a, that is f dash x has the same sign in the complete neighborhood of a, then a is neither a point of local maxima nor a point of local minima. In fact, such a point is known as the point of inflection. Based on the first derivative test theorem, we can find the following algorithm to find the points to local maxima or local minima of the differentiable function. The first step is to put y equal to fx. Second step is to find dy by dx. Next is to put dy by dx equal to 0 and solve this equation for x. Now here let c1, c2, c3 up to cn be the roots of this equation. Then we are going to test the function at each of these points to find the possible value of maxima or a local minima. Next consider x equal to c1. If dy by dx changes its sign from positive to negative as x increases through c1, then the function attains the local maxima at point x equal to c1. And if dy by dx changes its sign from negative to positive as x increases through c1, then the function attains the local minimum at point x equal to c1. And if dy by dx does not change its sign as x increases through c1, then x equal to c1 is neither a point of local maxima nor a point of local minima. In this case, for x equal to c1 is a point of inflection. In the similar manner, we may deal with the other values of x. Next, we are going to discuss a problem that would be based on finding the value of the local maxima or local minima of a given function. Here we have a problem which says that find all the points of local maxima and minima of the function fx equal to x cube minus 6x square plus 9x minus 8. Let us consider y equal to fx, which is equal to x cube minus 6x square plus 9x minus 8. Then dy by dx, which is the derivative of function fx, is equal to 3x square minus 12x plus 9, which can be written as 3 bracket x square minus 4x plus 3 bracket closed. Now for a local maxima or a local minima, we should have dy by dx equal to 0, which implies that 3 bracket x square minus 4x plus 3 equal to 0. This gives us the value of x as 1 and 3. Now we have to examine whether these points are points of local maxima or local minima or neither of them. So we have dy by dx equal to 3 into x minus 1 and x minus 3. The changes in the sign of dy by dx for different values of x are shown in this figure. Now clearly dy by dx changes sign from positive to negative through 1. Therefore, x equal to 1 is a point of local maxima. Also, dy by dx changes sign from negative to positive as x increases through 3. So x equal to 3 is a point of local minima. With this we conclude another lecture based on applications of derivatives that was based on the maxima and minima of a given function.